Hi friends, welcome back. This is Santosh Kumar. So today we'll continue with the root locus rules. In the last class, if I'll give you the brief summary of that, we have taken 3 rules, correct? Let me go over there. The first rule was the root locus is always symmetrical about the real axis. You can see over here I have drawn 3 root locus for different systems. The root locus, whatever I have drawn, is symmetrical to the real axis, isn't it? So it will be always symmetrical, correct? The second rule says the number of loci, or you can say these are the root locus branches. Okay, the root locus branches, these are the root locus branches. You can say it's loci or loci or whatever. Okay, so depends on number of poles and zeros. Okay, if poles are greater than z, so number of poles is equal to the number of loci. What it means, in your system, if you have poles equal to 4 and zeros are 1, so you'll be having 4 RL branches definitely there. Means if poles are greater than zeros, then number of poles is equal to RL branches. Similarly, if you have zeros are greater than poles, then number of zeros is equal to number of loci. Okay, the third rule was very important. Real axis loci are the RL branches. How to find the RL branches? A point exists on RL branch if, wait a minute, let me take the marker over here. A point exists on the RL branch if the sum of poles and zeros to the right hand of that point, means if you are choosing one point over here, let's take this as the point. Okay, so what I'll do, I'll see in the RHS, if the number of poles and zeros available in the RHS in odd form, means they are odd, then only there will be RL branch between these 2 points, isn't it? When I'll come over here at 2, I'll check in the RHS number of poles or zeros. The summation I'll check. Over here you have 2 poles, so 2 is even number, so I'll not have any RL branch over here in between them. Okay, then I'll switch to the infinity. Why I'm going to infinity? As I told you earlier, if you have p greater than z, so remaining z will be available on the infinity. So at the infinity, the number of points in the RHS 1, 2, 3. So again you have odd numbers, so between this and infinity I'll be having one root locus branch over here. I think it's clear to you. So today we'll see the fourth rules. Okay, let me take the pen over here. Okay, so today we'll see the asymptotes. What are the asymptotes? See friends, suppose, let me draw the diagram over here. See, in this graph, this is the RL diagram, root locus diagram for the particular system. Okay, the root locus branches like this, it's are going to the infinity. So these branches are going along with this. You can see these 2 lines. These lines are nothing but the asymptotes. So what is the definition of these lines? These are the branches which are approaches to the infinity. These are heading towards the infinity. These branches we call the asymptotes, and the number of asymptotes is equal to the n equal to p minus z. Okay, what it means? See friends, so number of branches which are heading to the infinity. So alongside of these asymptotes, I'll have root locus branches, which or I can say those branches will go to the infinity. Why they are branches moving towards the infinity? As we discussed earlier, suppose you have p equal to 3, number of poles 3, number of z, number of zeros you have 1. So you have deficiency of 2 zeros, because for the root locus we should be having p equal to z, pole should be equal to z. If we have deficiency of any one, we'll assume that particular thing on the infinity. So what it means, z equal to 1 is okay. Remaining two zeros will at infinity. Okay, so here the condition is fulfilled that p should be greater than z, means a proper transfer function for the root locus, all this assumption. Okay, so how many numbers? See, what I mean is, let's take, you have 3 poles, -2, -1, -5. You have only one 0, that is at 0 itself. Okay, now you have 2 remaining zeros, definitely they will be on infinity. Now what are the number of asymptotes? How many lines you require to take your RL branches to infinity? Only 2, isn't it? So the asymptote is nothing but those lines which take your root locus branches to the infinity, and it's given by p minus z. Your p is over here, number of p is over here 3, number of zeros 1, so you have 2. So 2 asymptotes. So definitely we have 2 zeros, and 2 zeros are at infinity. So definitely you require 2 lines. So this is the formula for the asymptote. I hope it's clear to you. Okay, now what is the angle of asymptote? See friends, at what angle this asymptote will go? Will it will go like this or this? How to find out that asymptote angle? So that angle definition or the formula is that this is theta is the angle of asymptote. So I'll take it theta a, and it's given by 2q plus 1 180 degree divide by p minus z, means number of p minus number of z, where q is 0, 1, 2 up to p minus z minus 1. Okay friends, is it okay to you? So this is the angle of asymptote. Wait a minute. The angle of asymptote, the angle, these lines, see this line, these are the asymptotic lines. These lines are making the angle with the real axis. This one, this angle is given by theta a. The formula is 2q plus 1 into 180 degree divided by p minus z, where p is the number of poles, z are the number of zeros. Okay, is it okay to you? Now one more thing, at what point it will start? Your asymptote, at what point it will start? So that thing is nothing but the centroid. We'll discuss about that. Let me take the pen over here. The next point is the asymptote must be symmetrical about the real axis. This is the point. The point for the asymptote must be symmetrical about the real axis. Why symmetrical? Because asymptote will carry the RL branches, and we know the RL branches are symmetrical about the real axis. So definitely your asymptote also be symmetrical about the real axis. I think this point is clear to you people. Now the asymptote gives the direction of zeros. What this asymptote is showing, see, we know that at z equal to, suppose at infinity, means your poles are moving at zeros or not. As we discussed earlier in the starting of the root locus, your poles are starting at k equal to 0, means your root locus are starting from the poles and terminating at zeros at k equal to infinity. We have seen this, isn't it? Means we are moving to the zeros. We are starting at the poles, we are moving to the zeros. So definitely your asymptote gives the direction of the zeros when p greater than 0. I think this point is clear to you people, isn't it? Now let's come to the next point, and that is centroid. So what is the centroid? See, related to this particular, let me take it over here, related to this particular asymptotic line, we have seen one thing, that is the angle of this line to the real axis. Okay, then we'll see at what point this asymptote will start on the real axis. So that particular point is nothing but the centroid, and that centroid is given by, let me take the pen, that centroid is always, so let's come to the definition first. It is the intersection point of the asymptote to the real axis. Okay, no problem at all. Let me draw the diagram over here. Suppose this is your asymptote. Along to this asymptote, your root locus branches are going or heading towards the infinity. So the intersection point of this asymptotes on real axis is given by this sigma called the centroid. Okay, and the centroid is nothing but sum of real part of poles minus sum of real parts of zeros divided by p minus z. Means you can write it over here, real parts only minus and z real parts divided by p minus z. Here these are the numbers. Okay, these are the numbers. Is it okay to you? Means suppose in a question you have poles, let's take -2 plus minus j. You have two poles, isn't it? And you have 0 that is equal to -3. Now suppose you are calculating sigma, so we'll take the real part of your poles. So -2 minus 2, 2. We'll not consider this. Okay, summation you need. So I'm taking summation of two poles, this minus sign over here, summation of z means zeros, minus 3. So this is -4 plus 3. So at -1 you will get the centroid. What centroid means? The centroid means your asymptote will intersect at -1 on the real axis. Is it okay to you? Now the point related to this is, wait a minute, the centroid may be located anywhere on the real axis, may or may not be on the RL branches. What it means? See friends, what is this point all about? See, suppose let's take like this. Okay, perfectly fine. Let me change the color. So let's check the RL branches. I'm coming to this point. I'm not getting anything in the RHS, so no branch will exist over here. Over here, when I'll come, I'll watch to the RHS and I'll get 1 point, that is 1 0. Definitely I have one RL branch in between them. Then I'll come to this point, I'm getting 2 points, so I do not have any RL branch over here. When I'll come to this, I'll be having one RL branch. So RL branch, isn't it? Now what this point says, what this note says, the centroid may be or may not be located, may be located anywhere on the real axis, may or may not be on the RL branches. Means your centroid may start from this point and this point is not on the RL branch, or it may come over here. There is no such foundation that their centroid should be on the RL branches or the centroid should not be on the RL branches. Is it clear to you? Now I'll take one problem over here, so everything will be clear to you people. Okay, just wait. So here is the question given, calculate the angle of asymptote and centroid. This is the open loop transfer function given. As we discussed earlier, in the root locus we need the open loop transfer function only. If I'll talk about the RH criteria, I need the characteristic equation there. Okay, so you have to calculate the angle of asymptote and the centroid. If you will calculate the centroid, that is denoted by sigma, the summation of p minus summation of z divided by p minus z. These are the number of. Correct? So what are the poles you have? A is equal to 0, -5 and -10. These are the poles you have, isn't it? Now the sigma is summation of poles, that is 0, -5, -10. Do you have any 0 over here? No. So it's a 0. Divide by number of poles. How many? You have 3. So it's 3 minus number of zeros. You have 0. So finally you have -5 -10 divided by 3. That is -5. Isn't it? So your centroid will be -5. The first, this answer is okay. Now let's come to the angle of asymptote they're asking. We have seen the formula. the formula is the angle of asymptote is nothing but 2q plus 1 into 180 degree divided by p minus z, isn't it, where q is starting from the 0 and going to p minus z minus 1. Okay, so let's find out the q value. 0, p, how many? 3 minus 0 minus 1, means from 0 to 2 it will go. 0, 1 and 2, 3 values we will take for this particular one. Okay, and easily you can understand, you have how many poles over here? Only 3 poles. You don't have any 0, so all zeros will be at infinity. All zeros will be at infinity, so you require 3 asymptotic lines, so you will be having 3 angles. Okay, find out the individual angles. Let's find out theta 1 first. Put the q equal to 0 over here, so 2 into 0 plus 1 into 180 degree divided by p minus z, number of poles 3, number of 0 0, so that is 180 divided by 3, so you are getting 60 degree. Let's find out theta 2, so 2 into 1 plus 1, okay, into 180 divided by 3, so put q equal to 1. Okay, we have done this. 2 into 3, so 3 times of 60, that is 180 degree. Let's find the theta 3, so it will be 2 into 2 plus 1 divided by 3 into 180 degree, so you will get over here 300. So these are the angles. Okay, so here I'm not doing the root locus because we need some more rules, then we can able to do the we can draw the root locus diagram. But if you want to see, I can draw how it will be like. Okay, so let's take number of poles, and okay, I'll take GSHS again, that is K S plus 5 S plus 10. Okay, so wait a minute, how many poles you have? S equal to 0, S equal to minus 5, S equal to minus 10. So here it is 0. Okay, here it is minus 5. Okay, and here it's minus 10. Okay friends, now the second rule, if you know, we'll find the RL branches. First we'll come to this point, we'll see to the RHS, is there any points over here? No points, so no RL branch will come over here. I'll come over here, when I'll see to the RHS, I'm getting one point or one pole, so definitely there will be RL branch between these 2 points. RL branch means root locus, means your poles are moving to the 0 by following this branch. That is this is the root locus. In the first class, if you remember, we discussed what is the root locus. The path of the root of the given function is nothing but the root locus, correct? Now I'll come over here. I'm getting 2 points. So this is the even number. I'll not get any RL branch over there. Then I'll go to the infinity. Why I'm going to infinity? Because at infinity I have zeros, number of zeros. Though over here zeros are not given, and we discussed for the root locus branch, for the root locus, the poles should be equal to zeros. This is the foremost assumption. Okay. So at infinity, if I'll come to the infinity and I'll see to the RHS, I'll get 3 points. 1, 2, 3. So definitely between these 2 points, I'll be having one RL branch. Okay. So this is the very first step to draw the root locus diagram. So we have done this. Now how many branches will go to the infinity? 3 branches will go to the infinity. Definitely. Why? Because number of poles over here 3, number of zeros you have 0, So asymptote, as we know, number of asymptotes is nothing but p minus z. 3 minus 0, so 3 asymptotic line you will get. Asymptotic lines means the lines which are heading towards the infinity at a particular angle, and we have find out those angles. The first one is 60 degree, the second one is 180 degree, and the third one is 300. Okay, so let me draw the asymptotic lines over here. But from where I'll start the asymptotic line? I need centroid or not? Can I take over here? Can I take over here? Anywhere I can take on the real axis, but for that I need the centroid. And we have find out the centroid for this particular question, and that is -5. Means your asymptotes will start from -5. Okay, friends. Now, how many asymptotes you have? 3 asymptotes. The first asymptote will go at the angle of 60 degree. At the angle of 60 degree, here it's a 60 degree angle, and this line will go to the infinity. Asymptote means it's going to the infinity. Okay? Okay, perfectly fine. This is the asymptote 1. Let's take it A1. Now, the second asymptote, this is A1, this is A2 and A3. The second asymptote will make 180 degree angle with the real axis and will head towards the infinity. So 180 degree. So this is fully 180 degree over here. So this asymptote will go to this side continuously up to infinity. So this is A2. Now what about A3? A3 is making 300 degree. So this is the 300 degree over here. This is 300 and it will go like this. Okay. So this is A3. So you have 3 asymptotes: A1, A1, A2, A3. A1 is making 60 degree. Okay, perfectly fine. How I'm getting that I have to make the 60 degree? Because I have already find the angle of asymptotes. The formula for the angle of asymptote we used over here is summation of p, 2q plus 1 into 180 degree divided by number of poles minus number of zeros. Okay. So I have found the angles. Okay, but I need the intersection point, that is nothing but the centroid. So that centroid I have found by the formula summation of p minus summation of z divided by number of p minus z. So over here I got the value, that is -5. So from the -5 I have 3 asymptotes. Why I'm saying I have 3 asymptotes? Because that formula I have also n equal to p minus z, that is 3 asymptotes I am getting over here. So 3 asymptotes will start at the point -5, will make 3 different angles: 60 degree, 180 degree and 300 degree. Everything is over. Now the 2 branches over here, see, the one RL branch is already going to infinity along A2. Is it okay? As we know, asymptotes are the line along with the RL branches will go to the infinity. So for the A2, the RL branch, this one is going to the infinity. But for these 2 lines, I need 2 more RL lines. Okay. So let me change the pen over here. Okay. Wait a minute. I'll take this one. So these poles, this is the RL branches, these poles will come to this. Later we'll know about these things, and over here they will break because 2 poles you have, and finally they will head towards the infinity like this. This is not part of our rules, it will come, so wait and watch. So this will be your root locus. This is the final root locus, where this one is also RL branch. So this is my root locus diagram, RL diagram. Okay friends, so let's come to the next concept. Now the concept is the breakpoints. What are the breakpoints? Friends, see over here, in this question, when we draw the root locus branches, what we have seen, we have 3 poles, 0, -5, -10. Okay, perfectly fine. I'll start my journey from the poles, isn't it? Why? Because at k equal to 0, the root locus will start from the poles, and at k equal to infinity, it will terminate to 0. 0 means zeros, okay? Poles and zeros, okay? So I have 2 poles over here. I cannot go this side. I cannot go this side. Why? Because in between them I have root locus branch. Means they'll follow this root locus branch, okay? They'll come over here. This one is coming to this side. This one is coming to this side. And at particular point, they will break. Why? Because they have to go to infinity. Why they are going to infinity? Because they have to meet to zeros. Correct? So, they have to break themselves over here on the real axis. So, this point is nothing but break away point. Okay? Suppose instead of this, the scenario is like this. This all are the zeros. In the numerator, all these points are given. So, here you have -10 is 0, this one is 0, this one is 0. The RL branches will be same as it is. Now, the poles will be at infinity. Now, this root locus branches will come to the 0. What I mean is, see, wait a minute. Over here, this time, these poles are going like this. This is the direction. They have to go to the zeros at infinity. They have to terminate themselves. Like this, they have to go. This is our root locus. Over here, k equal to infinity, that is nothing but our 0. Okay, now the scene is different. Like over here, it's going to this side. Now the scene is, instead of this poles, you have the zeros. So if this will be 0, the scene will be like this is 0. Over here, it's 0. Over here, it's 0. The number of root locus branches will be same. Like this. Now you have 3 poles, and those poles are at infinity. Everything will be same, asymptote will be same. Now from infinity these branches will come. These branches will come. Now these 2 poles, the poles are coming, isn't it? Now the poles are coming k equal to 0, and at 0 it shows k equal to infinity. So it will come over here. So 2 poles are coming. This is the direction. They are meeting over here on the real axis. This point is called the break-in point. This point is break-in point, isn't it? So I think it's clear. Okay, if you have any doubts, so it will be, die out when I'll come to the problem. So the point at which 2 or more poles meet directly at any location is called the breakpoint. Now we have 2 things, break away point. At this, poles will leave the real axis. Over here you can see the poles are leaving to the real axis. Okay. So this point is break away point. Break in point, at this, poles will enter to the real axis. I hope it's clear to you. Now note one thing. And one more thing, 2 or more. There may be 3 poles, 4 poles, 5 poles, whatever, but it should be greater than 2. The note point is the RL branches leaving or entering real axis, at an angle of ±180 degree by n, where n is the number of poles. What I mean is, you will understand over here. Let me take the pen. Okay. What I'm saying is, see over here, at this point, how many poles are meeting? 2 poles definitely. Now they are leaving this real axis. So at what angle they'll leave? That angle is nothing but, let me take the pen. That angle is given by this angle by which they are leaving the real axis. This theta is given by ±180 degree divided by n. N is number of poles. How many poles meeting over here? Don't consider these poles. The poles which are meeting, 2 poles, so ±90 degree. So they will start like this at 90 degree, and they will move towards the infinity like this. So this angle I'm talking about, isn't it? Is it clear to you? So now we'll see the location of breakpoints. Okay, definitely you'll ask me this question. The location of the breakpoint, see over here, at what point the poles will break out, over here or here. This is entire RL branch, and anywhere I can get the breakpoints, but where exactly? So how I'll find out that? Here is the procedure. You have to form the characteristic equation, that is 1 plus GS HS. This one is given into the question, so you have to form the characteristic equation. Then you have to rearrange in the form of K equal to Fs. Means you have to take this K aside and we'll make the Fs. Then next you have to differentiate this K with respect to S to make it 0. And to make it 0 means dk by ds you will find out and will equate to the 0. So this is your equation. You will find out the roots of this. So the roots of this equation will give you valid and invalid breakpoints. What is the valid and invalid breakpoint? So valid breakpoints are the points which are, on the RL branches. What I mean is, when you will find out dk by ds, you will get some values like in between -6. Suppose you are getting one value at over here, and one value you will get over here. Which one will be the perfect one or the valid one? Definitely, because your RL branch is over here given, so your breakpoint should be over here or outside of it. So definitely this one is valid. So valid is the point which is on the RL branch is the valid breakpoint. The point which is not on the RL branch is invalid, isn't it? So friends, this is all about today's class. In the next class we'll see some more 2 or 3 points, then we'll switch to the problems. So you can subscribe the LGF. You can find us on the Facebook for the doubt solving. We'll meet in the next class. Till then, take care and bye.